All right, in this video, I'm going to quickly review over gas laws. If you'd like a little bit more of a detailed lecture about the gas laws, you can go watch my videos in my chemistry playlist, but we're just going to talk about them quickly here. Um, there are four different laws that we'll talk about: Boyle's, Charles, Gay-Lussac, and ideal gas law. And then I'll also mention combined gas law, which really puts together these top three. So the first is Boyle's law, and Boyle's law says that gas volume is inversely proportional to the pressure applied to it. So that is, if you push on a gas, it's actually going to make it smaller and decrease the volume. So here you can see this like inversely proportional relationship. We get this curve here as we double the pressure, it's also going to decrease the volume by 1/2. Right, so the greater the pressure, the less the volume, or the greater the volume, the less the pressure. And if you think about this in terms of an example like a scuba tank, if we know from studying fluid physics, as we go underneath the water, we add pressure because of the water column above, the gauge pressure, and so that would cause the gas inside a scuba tank to become smaller. Now, if we look at it mathematically, we can look at it like this, where pressure times volume is equal to pressure times volume, whereas if you change the pressure, it will affect inversely the volume. All right, then we have Charles' law that relates gas volumes and temperatures, and in this case, temperature and volume are directly proportional, meaning that if you heat up a gas, it will expand and get bigger. So as the temperature increases, so does the volume of the gas. And likewise, if you were to cool the gas, then the volume would get smaller as well. And this will come into how engines work, and we'll talk about that when we talk about thermodynamics and how the volume of a gas can then, and changing the volume of a gas can do work on a system. All right, so mathematically, if we look at it, it would be volume over temperature is equivalent to volume over temperature. So if volume increases, temperature will also have to increase to keep this expression true. Then we also have Gay-Lussac law, which is relating pressure and temperature. So gas pressure is directly proportional to the absolute temperature of the gas. The greater the temperature, the greater the pressure. The lower the temperature, the lower the pressure. And this makes sense because we talk about gas pressure resulting from the particles hitting the side of the container with which they're in. We know that pressure is force per unit area. So if we increase the temperature of the gas, the particles are going to move a lot faster. They're going to strike the container with greater force and therefore exert more pressure. So the equation here showing again that direct proportionality. You have pressure over temperature is equal to pressure over temperature. Now, this is three different variables that are all intertwined with one another. So really, when we're going to think about it, we would think about it in terms of the combined gas law, where all of three of these could change at any one moment. So pressure times volume over temperature is equal to pressure times volume over temperature. So what this means is that PV, or pressure times volume, is directly proportional to the temperature. Now, in some cases, we will keep a variable isolated or constant. So if we have a certain size container where you can't change the volume, or if you have something that's thermally isolated where the temperature cannot change, and we'll look at that when we talk about thermodynamics as well. But just remember that all three of these variables can be changing at the same time. All right, the last gas law I'm going to talk about is ideal gas law. And the ideal gas law is that PV equals nRT, which you probably recognize from chemistry, where N is the number of moles and R is a gas constant. And a mole is an amount of a substance, and we can figure out how many moles of a substance we have from the mass of that substance and knowing the identity of it. So to find moles, we would take the mass of the gas and then divide it by the molecular mass of the gas. And again, you can go back and watch more detailed video about molar quantities if you want, but we don't really need to know this in too great of a detail for chemistry. But this really just kind of relates the pressure and the volume and the temperature to the amount of the gas that we have. Now the gas constant is 8.315, and we're missing a variable here. I think it should say atmospheres or kilopascals. We'll look that up on the front of your reference table, but it's a constant value, and sometimes there's different numbers based on what type of pressure unit you're using, whether you're using kilopascals or atmospheres or even millimeters of mercury sometimes in chemistry. But again, it's a constant and it's a value that will be provided for you. Now, the last thing I kind of want to mention about ideal gas law is, remember in a previous video we talked about the internal energy of the gas being related to 3/2 the mole times the gas constant times temperature. So we can see that the internal energy and the pressure and the volume are related to one another, and this will come back as we look at thermodynamics. So I'll go into more detail about it then, but I just kind of wanted to point that out, that recall that these equations are pretty similar to each other, and we'll talk about how they're related later. All right, so we know that if we heat up a gas, it expands, but do other substances expand? And the answer is yes. So when we heat up a material, it will expand, and when we cool it, it will contract. Not quite to the extent that a gas does, but in some sense that it creates somewhat of an issue for us in terms of, building structures and things. So if you are building a bridge, for example, which is what I'm going to talk about in a second, and you make it of concrete and metal, well, what's going to happen if it heats up? It's going to expand, or if it cools, it contracts. And structurally, what will that do to the bridge? We need to make sure that our bridges aren't going to buckle and break, based on temperature extremes. Now, the only material that's sort of the odd one out for the idea of thermal expansion is water. So as water cools, yes, it does contract or become more dense, but there's a point at about 4 degrees Celsius where it actually starts to crystallize and to form ice. And ice is actually the solid form of water, is less dense than liquid water. And it's the only material that solid form is less dense than its liquid form, and therefore floats rather than a solid sinking to the bottom. So what determines how much a substance will expand? Well, we can actually calculate it, and it has to do with a constant called the coefficient of linear expansion, or we can look at it in terms of volume and look at the volumetric expansion. And down here we have the equations, and really what this is the final length of something, linear length of something, is equal to, so whatever it initially started at, and then you have this coefficient of linear expansion. So it's the amount it will expand based on the change in temperature. So this is a value for a given material. We just have to know what that type of material it is, or be given this coefficient, multiply it by the difference in the temperature, and then add it to 1, and that's what we're increasing our initial length by to get our final length. And the volumetric equation is very much the same, but we're just talking about volumes. So you have the final volume being equivalent to the initial volume, 1 plus, and you have this Greek letter beta, which is the volumetric coefficient. But again, you'd need to know what the substance is, and that's just a value that is known. So to just give you a couple examples then of how this applies, right? Opening a tight metal lid. So if you have, a jar of pickles and you can't get the lid off the top, what you can do is you can put it under warm water. And as you put it under warm water, it causes the metal to expand. And as the metal expands, it pulls away from the glass, and then it's easier to open up the lid. This right here is a grid that's used in a lot of roads or in bridges. And really what this does is it allows for the linear and volumetric expansion of the concrete, and to keep the bridge from buckling. So if it gets too hot and it starts to expand, then the concrete can crack and can mess with the structural integrity of the road. All right, so those are the ideas of gas laws as well as thermal expansion in terms of solid materials.